Okay. Hello, everybody. Just a quick reminder what happened yesterday. Yesterday, it was a lecture on how orthogonal polynomials appear in the picture of the Ising model, Planar Ising model, and how one can use the structure of, okay, the spin disorder variables, but better to say of discrete fermions. I'm going to comment slightly more today on this, to do computations. And an analogy to have in mind, just if you want just one punchline of the whole story, this would be the following. So there is a parallel. Imagine you, okay, doing classical probability and you are interested in something related to random walks. I don't know, some question. It is not necessary, it might be not necessarily a question about random walks themselves, but it might be some lattice model like uniform spanning trees or loop erased random walks or something like that. Then what you should expect is that there is a structure of discrete harmonic functions behind, right? Because we all know that natural quantities on a graph like the green function basically, or heating probabilities or something like that, those all are discrete harmonic functions on a graph. And then one of the ways to attack your model is just to think about these functions. Okay, just analyze them. And the parallel with the Ising model is the following. So in the Ising model also there is a structure of functions. And those functions, those are typically correlators of chi, c, blah, blah, blah. So these are observables. And that's the same level of, I mean, that's the tool of the same level. So analyzing such functions, you can gain information about the model. So yesterday it was example in the full plane. And for today, this conformal invariance and criticality, I'm going to give precise definitions. So what will be the underlying lattice for today? It is a generalization of the square one, so-called rhombic lattices or isoradial graphs. The last name is due to Kenyon, I believe. If you wish, you might think just about the square lattice or hexagonal grid or some favorite tiling of a plane by rhombi, if you wish. It is not necessarily assumed to be periodic. You might think about Penrose tilings, for instance. Okay, so rhombic lattices, isoradial graphs. Okay, let us assume that I have an infinite tiling of a plane by rhombi. I do not make any assumptions about periodicity, but I always assume that angles are not too small, that all the angles are bounded from below. Well, that's a technical assumption, and by the way, it's an interesting question to which extent it can be removed. I do not know a precise answer. But okay, it's simpler from technical perspective to work when all the angles are bounded below and bounded away from pi. So then, where is the Ising model? Starting with such a lattice, what you do, this is a bipartite graph, of course, what you do, you mark every second vertex. And the graph on which we play our games is here. So this orange graph is my graph G. Well, I hope that the colors are visible, but okay, I explained the procedure. Okay. So this orange graph is a graph G. And it is called isoradial. I mean, why the name isoradial? Because every face is inscribed to a circle, and here is the center of the circle. Okay, what I also should do, I should specify the weights. And the weights, now what I do, I say, okay, each rhombus has an angle. And let me say that theta is the half angle. That's exactly the setup of the problem 4 in the first set of problems. And then what I say, okay, let it be theta e, let the weight, Ising weight of this edge is tangent theta e over 2. Well, that's a good question. Well, there are two global choices, right? I mean, the rhombic lattice is a bipartite graph, so I just choose vertices of the same color. That's a global procedure. So I might have chosen other half of vertices. And that's the duality of the Ising model. So if you think about the spins disorders, so what happens in my notation is that spins are assigned to these vertices, I mean to uncolored vertices, and disorders are assigned to orange vertices. But this is a self-dual picture. So what you can also think about is the Ising model other way around on the other color. Okay? So somehow you should think about rhombic tiling as about a couple of a graph and a dual graph. Okay, so here is the dual graph. Okay. And okay, as we discussed this, just a simple remark. So provided, so yet again, just to emphasize, this is the same notation as I used yesterday when I said let theta be twice or inverse tangent of x. But now the thetas, they also gain geometric meaning. They just capture some geometric information. And if you think, for instance, about the square lattice, then all those rhombi, those are just squares. So theta is just pi over 4, and this is the critical weight of the Ising model. Okay? In general, this is called critical z-invariant Ising model. What this z-invariance is about, that's about third triangle moves. So probably most of you have seen such pictures in this or that context. So what you can do with rhombic lattices, you can play third triangle moves. You can say, okay, third triangle invariance. Third triangle or Young-Baxter moves. You can say, okay, provided that, well, not provided, okay, provided I have a vertex of degree 3, so provided somewhere I see such a local picture, and this was my graph. Okay, I can do a flip here. Say, probably you are familiar with stylings by lozenges. There it is just removing or adding the cube to the picture, and here is exactly the same, so there is no need to assume that all the lozenges have are of the angle pi over 3. So you can do a flip and do it like that. Okay? And to replace your graph, I mean, this star by triangle. That's why the name star triangle. So this is another Ising model on a new graph, right, which differs from the original one just by this local piece. And the message is that the Ising model is invariant under such moves. The probability distribution with these weights, with these special weights. So more generally, so what I'm going to discuss is a critical model. More generally, there is a one parameter family of weights. I mean, instead of tangents, it should be elliptic functions. So what you can do, you can say, okay, I have one global parameter for these elliptic functions, and then I have a family of weights assigned to edges. So this is still a quite rigid setup. So it looks relatively flexible, but what I want to emphasize is that this choice of weights is very, very special. And for instance, if you ask what happens on just general, say, periodic graphs, typically there is no hope to draw your graph, so I mean your weighted graph we equate with axis, so that this identity holds. But still, this is a nice example, and let me write it on the blackboard. What I already said is that the probability measure, except that, okay, here something changed, outside of this cube, it remains unchanged. So, my measure remains invariant. Well, I don't have many clues about what is the content of the second week, but I believe it should be relevant for the course of Paul Zinjustan. So I'm not sure. So that's a typical, I mean, that's the basic example in which all these R matrices appear and all these Young-Baxter relations are relevant. Okay, that's the first remark. And the second remark is that though I'm not discussing the word critical, so what exactly criticality means in this context, because I do not have a single parameter beta in what I wrote, right? Okay. Anyway, what I want to point out is that this model is at least self-dual. So this model is self-dual. Because remember, yesterday I commented that the duality between x and x star, so if we have this duality x exponential minus 2 beta j hyperbolic tangent beta star j star, and if I introduce the dual weight just by saying this is exponential minus 2 beta star g star, and then I take inverse tangent here, then the sum of angles is exactly pi over 2. So that's exactly what happens when I replace this this graph by the dual graph. So here, okay, if this is tangent p over 2, then this is tangent pi over 2 minus t over 2. So that's really a self-dual model. But again, in principle, there is no need even to have such a generality to discuss meaningful consequences. This was more to make a link with Young-Baxter story. Okay. And remember, during the very first lecture, I commented that the fact that the critical temperature on the square grid is tangent pi over 8, it is actually not a coincidence. So it has a perfect geometric interpretation. Just for the square grid, this theta is pi over 4. Okay? Now, let me start first by discussing what type of results on conformal invariance one might be interested in. So, okay, what type of results are nowadays available at the market? So basically, there are two objects to study, just quite different perspectives, which are of course related, but still of a different nature. So I'm going to speak about this perspective, which is correlation functions, pretty much in the spirit, say, of the previous lecture when we discussed correlation, just spin-spin correlations along the diagonal. Nevertheless, what I want to start with is to mention that there is another direction. So what is another direction? I might be interested in geometric description of my pictures. So I might be interested in how domain walls behave in the limit. Okay, so either correlation functions of something, fields in the lattice, in particular spins themselves, or geometric objects, say geometry of domain walls. Okay, to speak about conformal invariance, one, at least being a mathematician, would like to see conformal mappings involved somewhere. Okay, so what is the setup I'm going to work with? I always assume that there is a fixed domain in a plane, just a general shape, and that I have a discrete approximation to a given shape. So this is an approximation to omega, which is a fixed domain. Certainly, one can think about even more general setups, like not necessarily simply connected domain, like on the picture. And to emphasize that this is discrete, I'm going to just indicate it like that. It might be not necessarily simply connected. One might also think about Riemann surfaces. Anyway, I'm going to, well, in what follows, I'm always stuck with this simple setup. Now, what is delta? So delta is a mesh size. So for those rhombic lattices, there is a natural meaning of what the size of the mesh is. This is just the length of all the rhombi. So the length of sides of all rhombi. So common length. That this is delta. Still, you might wonder whether we should impose some regularity assumptions near the boundary, like the way how the mesh approximates the domain. Say for the Dirac model, you might have heard that this is of huge relevance. For the Ising model, it is not. So it is absolutely irrelevant in which way you choose to approximate a continuous domain by discrete ones. Okay, here on such a sequence of discrete domains, or just a family of discrete domains, I consider my Ising model, and again, for simplicity, I consider it with plus boundary conditions, say. Then, what the geometry of domain walls is about. Okay, here in discrete, we can simply draw all the domain walls. This is going to be a collection of loops, okay, more generally of even subgraphs. And I can, well, more precisely. And I can wonder about, is there any way to describe a limit of this random ensemble of loops? Say, okay, assume for a moment that we are on a hexagonal grid, so there is no issue with double crossings. So even subgraphs are just collection of loops. And I can wonder, is there any way to describe the limit of this object? And the message is that, yes, there is a way. So it is called conformal loop ensembles. Well, that's a particular example of such a conformal loop ensemble in the limit. Or you might have heard the name Schramm-Loewner revolutions. I'm not going to comment, evolutions. The acronyms are CLE and SLE. Yep. Yeah, so yeah, that's a very good question. Yeah, that's a very good question. So let me try to give an intuition. So first, let me distinguish between the length of a loop and the size of the loop, say diameter. So the first question is, indeed, do we expect that there are macroscopic loops at all? So what we should expect is that there are many, many microscopic ones, many, many very small ones, right here and there, just surrounding a single spin of a different color, for instance, of a different value. So the answer is yes, there are macroscopic loops. So to formulate the statement, convergence of this collection of curves to there, okay, what I'm saying is that this is the convergence in the most natural topology you can imagine. So here there are macroscopic loops. You compare them just one by one, and it means that, okay, you can make a bijection up to the set of small loops. Okay? So there are macroscopic loops. Okay, there are nested macroscopic loops. So in continuum, you really see a picture like that. Okay, that's of course a bad example, but okay, just collection of nested loops. Then the other side of the same question is, what is the length of an interface? This is a different question because interface, it so happens that in the limit it is fractal. So it is a fractal curve. So basically those continuous objects, they're composed of curves which have Hausdorff dimension 11/8. Okay, some interesting number. So those are fractal curves in the limit. Just, okay, yep. Yeah, I really don't have time to comment much on this. That's a topic of a separate class in 4 lectures, please. So, okay, I just wanted to indicate that, okay, you might have heard that there was a big buzz like a decade ago about Schramm-Loeffner revolutions and these conformal loop ensembles, and they do indeed appear in the limit of the critical Ising model. And the parameter, if you heard that there is a parameter there, okay, the parameter is 3, but it's like a meaningless statement if you never heard about what CL is, what SL is. Okay, some beasts, and they are labeled by real numbers. Okay. This real number is 3. Okay, I just wanted to make this remark. And what I am going to speak about is more results, well, not more, it's just results on convergence of correlation functions. And, well, what the plan is just to give several examples of what is available at this side. And these correlation functions, they're described by, I mean, they're given by what is known as conformal field theory. So that's a particular example of a conformal field theory, which one can actually construct by hand. And that's what I'm going to comment a bit. So that's conformal field theory. And now that's always a huge field. I mean, you can also wonder what is the link between this and that, and so on and so forth. So that's really a very, 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 very large research field nowadays. Okay. So let me give you a typical example of what is on the left. That's examples we are going to discuss how to prove. So, okay, I need some object, correlations of which I'm considering. And I'm going to speak about 2 objects right now. So the first is what is called the energy density. Okay, what is the precise definition? Given an edge, like that, I have 2 faces. So I have 2 spins assigned to the upper face and to the lower face. And then I need some slightly non-standard normalization. This is just a definition. I introduce a quantity, which is which is what I'm writing. So effectively, this is just the product of two spins. So I just take the product of this and that. And what is the product? Effectively, it encodes whether this edge is in my collection of domain walls or not, right? But I should normalize it slightly. This quantity. Yet again, this is just a shift and some additional normalization. So what happens in the square grid case? Then theta is pi over 4. So, okay, this is square root of 2. And actually, there is 1. So let me first formulate the result and then maybe make another comment on why one should subtract, say, exactly 1 in the square grid case. This is easily visible. Okay, what is the result? What we are interested in is just correlation of these quantities here and there. So what I fix a few points inside of my domain. Like, let me label them, I don't know, like A1, etc., AN. And what I consider is just the expectation. Let me emphasize that this is an expectation on this discrete domain with plus boundary conditions of the product of these variables. So I really want to know what the correlation functions are. Okay? And the claim I want to prove is that, there is a limit of these quantities. It should be added something here and there. Okay, first, what is the purpose of subtracting something? Basically, that's the expectation. So this thing is the expectation of the product of sigma sigma, and it does not depend on the domain. So provided boundary is far away in terms of the number of lattice steps. So remember again, here is a small mesh. So in terms of the number of lattice steps, all the points are very far away from each other as well as from the boundary, right? So what we should expect is that locally what we see is just the infinite volume measure. And I told you yesterday that at criticality there is just a single unique infinite volume measure. So okay, in this infinite volume measure, this quantity has some expectation. And this is the answer. So that's why we should correct. So because of that, right now, well, this doesn't look very meaningful, and actually one should rescale. And rescaling is exactly by delta per energy density. And the claim is that there exists a limit of such things. Okay. Let me now erase these conformal loop ensembles to avoid further questions on them. Okay, what are the properties of this limit? Of this. So the whole story should be about conformal invariance, or about how these quantities behave under conformal maps. So in the very first property is that, and the very basic one, I mean very important one, is that if I consider a conformal map to some other domain, like onto a square, which I'm going to denote eta prime, then these functions. So this is a funny notation. So you might be not very comfortable with this, but just think about this notation as a function which depends on the domain and on positions of this point, of these points, right? Instead of writing f, a1, etc., an, I just do as physicists do, right? So that's just a notation for an unknown function. And then the claim is that when I do a conformal transform, well, ideally, when somebody tells you conformal invariance, you should expect that this is really conformally invariant. I mean, that it doesn't change. But if you think for a while, this would contradict to this rescaling. So just, yeah, this is still not correct. So there is some factor. Yeah. Pardon? No, that's just a generic conformal map. What I'm saying is that for every conformal map, for every pair of domains and for each conformal map from one to another, this holds. So now let me comment again. So imagine, remember there the words scaling. And in particular, you can think about stupid conformal maps who are just multiplications by numbers, just dilatations. Okay, then if you're saying for a couple of minutes, you see that this and that cannot be consistent. To have a consistent picture, it should be the factor coming back. Actually, okay, to have a consistent picture, there is just no other way rather than to write such a factor. So, okay, they're not conformally invariant, but they're what people call conformally covariant, right? They behave like, I don't know, forms. Okay, that's not quite differential form because here there is an absolute value. Okay, they behave like if you are, well, you are young and your minds are flexible, so those are tensors of degree 1/2, 1/2 in both z and z bar. Okay, that's a nonsense basically, but okay, you are flexible. So that's the statement. And also another statement here, and by the way, I apologize, I forgot a multiple here. Here there is also a multiple. Right now, there is no contradiction, but the contradiction here is going to appear in the next line. There, I forgot a multiple. 2 over pi to m. In particular, by the way, this result is universal over all the rhombic lattices. You might say, okay, I'm cheating because this factor depends on the lattice. Okay, that was exactly the purpose to introduce it. I mean, just to have a result which is lattice independent in the class of rhombic lattices. So again, meaning for shape of what? In omega, but also in the lattice you consider. So it's the same result on square grid, on hexagonal grid, and on all isolated grids. So it is universal. I mean, yeah, the result is uniform and universal in everything. Okay, and now still you can wonder what is the precise form of this function. I mean, what the quantity is, and the answer is as follows. As I already said, it is conformally covariant, so to give an answer, I should specify it in one particular domain. And the standard example is just the upper half plane. So in the upper half plane, well, this function is purely explicit, and it is a Pfaffian of of something. And the something is also a very simple thing. It looks like I need to say something more. Okay. First, probably I forgot multiple I to n. Do I? Yep. It should be I to n somewhere. Okay. Here is the parity of n is not specified. So I have n points, and here I have a Pfaffian of a matrix whose size is 2n by 2n. The notation is that the first points coincide with a's, and another n points are just Schwarz reflections of the first ones. Okay, notation. Here is h, here is a1, etc. an. Here is an plus 1, which is an bar, etc. A to n, which is a1 bar. Just I to n, or here. I hope it is I to n. Yeah, not minus I. Just imagine n equals 1. Then this is what? This is just 1 over a minus a bar. So this is purely imaginary. You should correct somehow. Okay, so here is the result. And this result, I hope we will be able to discuss how to prove today and tomorrow. Is there any question? Yeah, that's a very good question. Thanks for asking. So ideally, what you want to say, you want to say this field in discrete is maybe just well, okay, that's fine. That's a discrete object, so it is something very very clear. So is there a way to define this as a random Schwarz distribution, right? Right. Right. Yep. Right. 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 But that's more a terminology, right? We can think about it, something like that. No, yet again, for me, there's still the question, can I define it? Because if you think about this as a Schwarz distribution in discrete, what you would like to say is that, okay, they converge, right? Otherwise, this is just introducing terminology. You should make some meaningful claim on them. In discrete or in continuum? But in discrete, that's a meaningless statement because this is a piecewise constant function. Of course, it is a distribution. There is only a finite number of values. Of delta. You mean it changes with... Right. Okay. But that's a finite combination of delta functions here. Of course, that's a distribution. Yeah, but... And what? Yes. Yes. Yeah, but that's exactly what I'm telling. You want to say convergence of distributions. And in particular, this must include existence of such a random distribution in continuum. And it does not exist. No.
I'm not asking about the interpretation of the left-hand side as the end moment of the random distribution.
Right.
I just ask, does the
does this distribution converges or not?
Endpoint function as a distribution, not as the moment of a random distribution, as a distribution of omega to the n, does it converge to something? In d prime of omega to the n.
Just concrete n moment function, you mean? Okay, just I fix all the points, and you. Okay, so is this random variable converges to something?
There is no random variable.
No.
On the left-hand side,
Yeah.
I see a function of the positions a1,
Okay.
a1 lattice.
Okay. Random function, or no? Just okay.
This is the deterministic function of a1, an.
Right.
So it's a function of the lattice.
Right.
But the lattice, I can see it inside. I can kind of associate multiply the delta function at the lattice point by
Okay.
this
By this quantity.
then I get for the left-hand side interpret that as an element of d prime of omega to the n, which depends on little delta.
Yeah, let us discuss later. I really don't understand what you want. Okay, let us discuss later. So my okay. Okay, here. Okay. Oh, I see. Okay, so what you want to say? Okay, let n be equal. Let n is 1. Then okay, this should be fine for you. So what you have expectation evaluated at each point, and then you just see it as a function. Yeah, as a combination of Dirac deltas, and you wonder whether this converges to something to the continuous measure with this density. Yes, the answer is yes. Just because this convergence is uniform in points and there are bounds in. Yeah. Okay, that's your question. I believe the answer is yes. I believe in this situation the answer, if you're interested in exactly this question, the answer is yes. So yeah, I'm not quite sure. Oh, there. Okay, sorry, I really didn't understand. Okay, so here is the result, and the message is that that's a relatively simple law, right? So there are just pfeffens. Why shouldn't we be surprised by pfeffens? Just because remember the very first lecture when I discussed dimer formalism of the model. So in the dimer formalism of the model, just the fact that here, there, and there, 3 given edges are present in the configuration is a pfeffen of a small size minor. Okay, there is a pfeffen process instead, and that's exactly the reason why here pfeffens appear. So now example 2 is just spins themselves. And here, to emphasize that we had some meaningful discussion on that field in quotes. Okay, and spin field, this is a more regular object. So what I can wonder is exactly the same setup, but with epsilons replaced by spins. Right? So instead of computing here effectively the probability that my edge is present in the configuration, what I can do, I just can ask, okay, what is the correlation of spins themselves? Well, that's not purely formal notation because A1, this is just a point in continuum, this is just a point in omega, and what I compute is actually this epsilon on an edge which is the nearest to this point, and the spin which is the nearest to this point. Okay, first question is how should I rescale? And the answer is that, okay, we already know. We already know that 2-point functions in the plane, they decay like the distance to 1/4. So n/8. Okay? If there were 2 points, then it should be 1/4. And it is reasonable to assume that it is just proportional to the number of points. And again, the statement is that, that's another theorem, is that this converges to some universal constant, and like this 2/pi, it does not depend on the lattice. So it is just the same on all the isoradial graphs. No additional normalization is required. Okay, now you might say, okay, here it was a fairly simple structure of correlation functions. So what happens with sigmas? And again, it is conformally covariant. So the same, the same covariance rule holds when you change the domain, when you apply conformal map. But obviously with 1/8 there. Otherwise it would be inconsistent. And basically the question is, what is the correlations in the half plane? Yep. Say again, I said correlations. No, it was dn. It was dn which was computed in factorials. Yeah, it was 1/4, exactly, but there were 2 points, right? It was sigma sigma. It was n equals 2. So that was 2/8, which is 1/4 in the. So I mean, if n equals 2, right, then what you should have delta minus 1/4. Because, okay, in my setup, the points are at constant distance in this picture, but in terms of lattice steps, it means that they have roughly delta minus 1 lattice steps in between them. Okay? So that's why it is consistent with the computation. Better? Okay. And okay, what is the exact formula in the half plane? Well, the message is that it exists, and it is not that easy. So this field is not at all Gaussian, and so on and so forth. So okay, let me write it down. But just to give you an idea of the level of complexity, it is not that complex, but it is quadratic irrationals in everything. Okay. Whew. That's just wait. I first want to write it down. There is no point, I mean, in copying it. You can Google it if you wish. 1/2. And U should be A indeed. Yeah. Oh, no. Now that's mess. Okay, you sum over all possible signs. Here is basically the cross ratio of a quadruple of points AP, AQ, AP bar, AQ bar. So all of them are, okay, that's like big sum of square roots of something, and there is a square root of on top. The signs on the line, so that's plus. Not because I'm in the half plane. I'm in the half plane with plus boundary conditions. That's yeah. In the full plane, there is a constraint that yeah, exactly. Okay, just okay. The formula is explicit if you wish. There are methods. I mean, if you open physical textbooks, you can textbooks, you can find a derivation of this formula. But on the language of conformal field theory, so somehow, which already assumes something about these functions in continuum. Okay, and now I want to spend some time just giving you, instead of proving these results, what I want to do is to give you some intuition about what is a proper way of thinking about these functions. And that's a different intuition from what you have in mind. Okay, so what is a possible way to think about spin correlations? And this is basically what is indicated in the problem number 5. So this bonus problem number 5 is exactly about this story. To give you this intuition, I want to step back to the discrete setup. So remember, in the discrete setup, in the combinatorics part, okay, there was the Ising model. And then it was a dimer model on this graph. So it was the graph GF. And then I told you during the first lecture, and actually it was also on the paper with definitions, that there are other dimer reformulations. So in particular, there is another dimer model reformulation which live on this non-planar graph. So I'm drawing a picture assuming that my original grid is just a square grid, but okay, you can do it for whatever graph you wish. And the idea is that the partition function of the Ising model, here this is just a pfn of some matrix. And this is not only a combinatorial bijection, you can also see it on the level of just algebra, of plane with matrices. So you can also compute, I mean, you can also see that matrices F and the adjacency matrix here and the weighted adjacency matrix there, they're related by simple transforms. Okay, so that's the partition function of the Ising model. Can be rewritten in this way. Still, that's not, okay, that's always nice, but there is a kind of a nasty detail. And the unsatisfactory detail is that both these graphs, they do distinguish G from its dual. So this picture is not self-dual. So vertices and faces, they play different roles. Combinatorially here they do not, but the weights actually are different. So here is 1, and here is x e minus 1. Just take a look on definitions if you have them. So, okay, combinatorially the graph is symmetric, but the weights are not. And that's, well, that's like, okay, can we do something further with that? And the answer is that we can do something with that. So there is yet another both combinatorial and algebraic trick. which allows you to pass to yet another graph. I apologize for so many graphs. So again, you have this graph drawn on the definition sheet, which now has twice more vertices. Okay. Is bipartite and planar. Now it's okay. There it's called GT. Two comments. So combinatorially, this is slightly more involved. So this is not like a bijection of a single configuration on this graph or of a single configuration of the Ising model with dimers on this bipartite graph. So combinatorially, you need two Ising configurations that corresponds a dimer configuration on GT. And the reference to here is exact Bazinization paper of Julien Zubeda. This is called exact Bazinization of the Ising model. You can find it at archive. Interestingly, it was never, as far as I understand, published in a journal. But okay, this paper exists and well known. And also there is an easier version due to Beatrice de Tullier. So just some combinatorial games. But if you think about just partition functions or something like that, you can do the same thing algebraically. And algebraically, what you can check, actually, I can, well, prove, but that's more to guess an answer and then to check it. So algebraically, you can say that, okay, some local matrix. What is a local matrix? This is just block matrix where each block is indexed by vertices surrounding the vertex of my original graph. So that's like block diagonal matrix. Block diagonal. Concrete block diagonal. Concrete block diagonal. Is again some local block diagonal multiplied by yet another operator D. And what is D? And D is nothing but, okay, to keep track of the size of matrices. So here matrix C, it is indexed by corners of my original graph. So here a graph has twice more vertices. So D now acts from black to white with a natural identification between them. Okay, and then take a look on this problem number 5. So what I'm going to do is just specify the weights. Okay, the weights here are sine and cosine. And here is 1. And in particular, the matrix 0D minus D0 is a Castellane matrix for this graph. Okay, so long story short, in this perspective, to compute the partition function of the Ising model on the original graph, you can also play with dimers here, you can play with dimers there, but you can also play with dimers here. And this is a fully self-dual picture, which is already good. Yep. they're better, I mean, this square case is self-dual. They better leave one on the original graph, the other on the dual one, but they're fully independent. And just you take two independent copies, and there is a combinatorial correspondence. But yet again, so there is no need to think about this combinatorially. Okay, for you it's of interest, but okay. In principle, there is no need to think about this combinatorially. There is just an algebraic identity which relates this matrix to that matrix. And when I think about determinants, these local matrices, they produce, okay, determinants are explicit factors. Okay. I want to make the next step. And the next step, I take for granted the material of problem 5, so just the conclusion of the problem 5. So what is the conclusion of the problem 5? Dmitry Chelkak. There. One can interpret this matrix after some twist, okay, twisted by something again concrete, conjugated by something concrete, is a discretization of the following operator. Just to give you an intuition, so what the operator D capital makes, okay, it computes some linear combination of these three values. Okay, the linear, well, a linear combination of three values, it might happen that it approximates derivatives, like derivative in x, derivative in y, provided all the complex factors they are adjusted properly. It might be a linear combination of dx and dy. And what I claim is that this is exactly an approximation of those continuous operators. And it should be, yeah, like that. Okay, so that's some story, but what at all does it have to do with spin correlations? So remember that spin correlations the actually ratio, so that was about the partition function, but to compute the spin correlation, what you should do, you should simply change the signs, flip the signs of x on cuts, and spin correlations, their ratios of 5n, say, of this matrix twisted by some signs over the 5n of the original matrix. Okay, that's a reminder from the first lecture. So from here, the picture should be as follows. So you should take this operator, and you should think about regularized in some way determinants of such operators, but with a twist. They should correspond to determinants. Let me put double dots just by indicating that it should be some regularization, which is a highly non-trivial one. What are those operators? where okay, this big operator here everything was antisymmetric or after proper modification self-adjoint or anti-self-adjoint. So this operator also looks like a non-self-adjoint operator, but one should specify what boundary conditions are. Acts on functions fg satisfying the boundary conditions like that, where tau is a tangent vector, unit tangent vector to the domain. An exercise to check that with such boundary conditions, this operator becomes anti-self-adjoint. And I should also say, okay, what happens with the puncture. So what you should do, you should think about this operator as acting on spinors branching over U1, UM. Because, okay, what the introduction of these minus signs mean? It means that you introduce a monodromy around a given, around each of these points. So this becomes, what's the message? I'm not going to go much further into this direction, but what is the message? The message is that there is a purely algebraic, if you wish, way of thinking about such an object. So you just consider such a domain, some boundary conditions, you consider a double cover of it, and there is this operator acting on the double cover. And the very last trick to do with this operator is the following. Assume we are now in the half plane. Assume we are now in the half plane. Then what you can do is the following. So instead of thinking about a pair of functions which are defined in the upper half plane, you can think about a single function which is f here and g bar z bar there. These boundary conditions, g equals tau f, reads just as f equals g on the boundary. So here I'm at the half plane, and here I'm at the full plane. So somehow, due to this boundary condition, I can glue two functions into a single one. And one can check that actually the operator which reads like that on the left-hand side, this is simply one d bar operator. So this was in H. This is simply d bar operator in C. So just considering this hand-waving idea of what this operator, of what the spin correlations are, what one arrives at is that it should be some regularization of just the d bar operator, which acts, okay, this is for the half plane case, which acts on the double cover of the full sphere, which is now ramified not only over u's but also over u bars. So here we have some points, and now doubled. Well, if you wish, this is a sort of an explanation why A and A bar there play the same role. Because algebraically, okay, well, in this interpretation, they're on the same foot. Okay, as you might have noticed, okay, that's of course is not math even. I mean, what I'm speaking. So to speak about this seriously, you really need to make a hard effort. I mean, defining objects. But well, in principle, yeah, if you, that's of course the hell is here is what regularization is. You can say, okay, I see this operator in discrete, if you wish, but this doesn't help much because what you, I mean, to compute those determinants, to get to that formula, what you really want to know is how these determinants, they behave when one starts changing points. Right, and this is not what we can directly see from discrete. It should be some intrinsic property of the construction in continuum. So what I'm saying is that there is a way to explain why the answer has this meaning, but maybe this is not what you want. You want somehow say other way around, that if I know that this fact for some concrete regularization, then I have a lot of properties of these correlation functions, and I can compute them. No, there is a continuous spectrum. Yeah. Oh, that's yeah. As you might have noticed, I mean, each lecture is somehow about a new material, and that's the idea of giving you links to some different research fields. And this is what leads to the theory of tau functions. So this is what leads to tau functions developed basically by the Kyoto School first. And again, coming back to the question you asked last time, that's exactly the way how you can think about all that in terms of isomonodromic deformations. Though, just unfortunately for the record, I should say that personally I cannot make it precise at the moment. I mean, the whole correspondence. So it's for sure it should work like that. There is a very nice book by Palmer where all that is discussed. But I would be unable to present it on the Blackboard if I've been asked. So sorry for that. But just to indicate that there is a lot of beautiful structures coming out, just erasing in the Ising model. Okay? Yeah, it is a Dirac operator if you wish. Yeah, well, you might, yeah. Okay, it is. And if you was out of criticality in the proper scaling regime, like what you asked last time, it would be, this is what is called massless Dirac operator, right? It would be some constant on the diagonal which changes the properties of the operator, of course. And then you can study how does this depend on positions of points, how does this depend on the mass on this constant, and so on and so forth. So that's exactly what what leads to all the Penleve stories and all that. Okay, yeah. So this is, let me stress it yet again, not at all proofs, just an indication. If you heard that Ising correlations, they satisfy Penleve equations that delimits the tau functions, and you wonder what is the reason for this, the reason is basically the partition function can be interpreted as a Pfeiffer or determinant of twice bigger matrix to an appropriate power, which is a discretization of either the bar operator or the Dirac operator or something like that. So that's just to give you a clue on the global landscape. Okay, now I still have 15 minutes. And this 15 minutes, I want to switch back and to do something much more concrete and to explain, okay, what are the tools to prove results, not like this, but what tools you need to develop to prove these theorems. Okay, so we are now going back to Earth from the outer space. Okay, so what are the tools? Main tool. Proofs of convergence result. Let me come back to the thing that I told at the very beginning about this parallel between harmonic functions, random walks, Ising model, this propagation equation. So there is a way at criticality one can interpret this propagation equation, which is a 3 terms relation on this double cover originally, is a discrete homomorphicity condition. Condition. It shouldn't be a big surprise in this phrase, because what I explained right before is that, okay, discretizations of d-bar operators appear somehow, so conceptually it shouldn't be a big surprise. Still, technically, there are several ways to do that, and among these several ways to do this, there is a particular one, most useful one, is due to Stas Smirnov, and it reads as follows. So basically, this is problem number 4, which you tried to solve last evening. At least some of you tried to solve last evening. So remember the picture. I'm going just to give a formulation. Okay, on this rhombus, this was V minus V plus U flat sharp. I can think about observables defined here and here, which depends on the corner. So this is problem number 4. And those are just omega expectation IT, etc. Okay, so locally these observables, they are functions, so I do not need to think about double covers locally. So those are just functions. And then the 3-term relations can be rewritten. So the propagation equation is actually equivalent to the following fact, that I can, to this quad Z generated by this H, I mean associated with this H E, I can assign a complex value such that these 4 values at corners are just projections of a single value, of a single psi Z. all 4 corners. So this projection means projecting in the complex plane. So in the complex plane, I have a complex number, I have a line passing through the origin, and I just orthogonally project onto this line. Check problem number 2. It is exactly what is written there. I'm not going to derive this equation, but what I want to indicate is that, well, okay, given a complex number, this is 2 real degrees of freedom, right? So basically, I have 2 real degrees of freedom for the values at these 4 corners, which is consistent because 3 terms propagation equation, it also leaves only 2 degrees of freedom. So at least it looks consistent. And those sine cosines, okay, it looks fine, actually. It's just a simple exercise to check. Why such a notion helps? Because imagine you want to prove a convergence result, say, for these absolutes. Imagine you want to say that psi approximates anything in continuum. Then you have a problem because, okay, on this concrete edge, psi, it has a prescribed complex phase. So this is real, and this is something prescribed. On this edge, it has another prescribed complex phase. Okay, what would be the natural conversion? What would be a way to formulate a convergence statement? So say here, let it be purely real, and here purely imaginary. In which sense this bunch of values might converge to a complex value? So here is one of the simplest possible ways. It turns out that there is a natural number associated to this quad. Okay? So that's the first ingredient. The second ingredient is that, in fact, well, this a priori, it is not clear, so that's a weird definition. Right now, for every quad, I have a complex number assigned to each quad. I have a complex number assigned here and there. Well, they satisfy some weird conditions, like projecting, I mean, like this and that have the common real part, this and that, they have common some other projection. What at all does it have with discrete holomorphicity? So 2 is the following lemma. Propagation equation implies the following result, that if I consider a discrete contour integral, okay, what is a discrete contour integral? I just multiply the value here by the increment there. Okay? So discrete contour integrals of this psi vanish. Okay, some stupid computation. So either, that's about systems of linear equations. Either this is a true fact or not. So, okay. What I'm claiming is that this is a true fact, and then that this is a stupid lemma, stupid computation to prove. And now you feel that you are in a good shape because you have true complex numbers written here and there, and you know that all the contour integrals vanish. So basically, if you are able to prove whatever precompactness result for such functions, then the limits are necessarily holomorphic, right? Because then the limits, they would also have vanishing contour integrals, right? So like, okay, think about a proof of a weak form of discrete harmonicity. That's exactly the same. Okay, so still there is a question how to get precompactness of these observables. And there is one more trick, which I want to formulate right now. Let me call it Smirnov's trick. There is a way to introduce yet another function into the game, so that's really a trick. On a given quad, let me define a function. So given a function psi, let me define the function h of this psi, which is now a function on vertices and faces of the original graph. And the rule is the following. Given such a local picture with one vertex, one center of the face, and the corner between, what I'm doing, I say that the difference the increment of the function between this v and u is by definition the value of psi at c squared. So a list of claims. Again, that's a simple check, but what I want to emphasize more is not exactly definitions and why this works, but what is the purpose of introducing this function. So this is going to be in 2 minutes. So the first comment is that this is a correct definition because, okay, I told you what is the increment here, what is the increment there, what is the increment here and there, and this should sum up to 0. So the first claim is that this is a correct definition. Exercises to check, but they are not going to be in the last exercise sheet. Some list of statements. This condition defines is well defined, meaning that H is well defined by this star. Second, you might wonder, okay, what would be the intuition about such a function h? Right? If I think about psi being convergent to something, what would be the limit of h? Is a discrete primitive in an exactly the same way as here, like on this picture. Okay, say on vertices. On vertices or separately on faces is a discrete primitive of the form imaginary part psi squared. Psi squared dz. So which means that if I want to compute an increment from here to there of my function h, then what I should do, I should square the value written here, multiply it by dz, and take the imaginary part. And up to now, this is a total nonsense because, and what? And what do we have from this function? I mean, what should we do with it? Note, however, that this is already somehow related with what is written above, though in a quite non-trivial way. So this function is constant along the boundary. So in continuum, you should think that, okay, we aim at proving convergence of psi to holomorphic functions. This should mean that H should converge to a harmonic function. And then you might say, okay, what are boundary conditions for these harmonic functions? And it's constant. Sorry. It's constant. And then here is an answer. So this function H is, in particular, a tool to work with boundary conditions. So, okay, those are Dirichlet boundary conditions. Dirichlet boundary conditions for H. And equivalently, boundary conditions of this form. That's why I told you that it is linked with what is written above for, okay, let me like that. Psi bar equals tau psi for the original function. And the last and also very important thing is that miraculously this function H provides you a tool to prove regularity statements. So there is some positivity. So there is some miraculous positivity. If I think about, so now my function is defined both on vertices and faces. Think about the square grid, for instance. Then it so happens that the Laplacian of H is always non-negative. And for this last effect, I do not have any even hand-waving explanation. So that's there. That's really a miracle. So I don't know. That's computation. Computation is not hard. You can find it in our joint paper with Stas for isoradial graphs about 10 years ago already. And on the square grid, it was just his observation. So that's Smirnov's positivity, I would say. Smirnov's positivity. Observation. And okay, this is on vertices. This is on faces. And altogether, so this gives you a set of tools. So here you miraculously see that, wow, this all has something to do with, say, subharmonic functions. But then, okay, probably everybody knows that, say, positive subharmonic functions, they're always a priori regular. So you can always estimate the L2 norm of their gradient in terms of the maximum itself. So this is just a source from where you can develop an a priori regularity theory for such functions. And then, just 2 minutes to conclude, what is the general not framework, what is the general root of the proof? You say, okay, I have functions like that defined on the lattice. My main idea should be to prove that they do converge to some limits which are holomorphic functions. From where I should take holomorphicity? Holomorphicity I take from this lemma that discrete contour vanish. The discrete contour integrals vanish. Okay, then how should I first prove existence of limits? For this, I need some a priori regularity theory, and this is, okay, some relatively, relatively involved story, but okay, it may be done. Then, okay, I have a limit. How should I identify what the limit is? First of all, I should think about boundary conditions. But boundary conditions, that's again a miracle with the function h. Function h has Dirichlet boundary conditions, and hopefully I can identify boundary conditions for the limit of the functions h. And then, okay, maybe I also need to identify some singularities and so on and so forth. But in general, at least I have like a road to go. So tomorrow, I'm plan to indicate just maybe one particular example of such a convergence statement, one or two, okay? Just to make, I mean, not details of the proof clearer, but rather making this scheme more concrete. What is exactly the object we are working with? What is exactly the limit? And what are the properties of this limit that, that can be obtained from such boundary value problems? But yet again, to stop, that's the scheme. So I should think about such functions. I should think about them as solutions to some boundary value problems. And here is the main magical tool to prove convergence of these problems. That's it. Questions? Okay. Thanks.